the previous episode, we learned that the position of a particle in the space is connected to the notion of a wave function. On this slide, you can see two graphs. The horizontal axis of each graph represents the space. For clarity, I consider here only one dimension of the space, but you can easily extend this reasoning to all three dimensions. The vertical axis here is the probability distribution of some random value. First, let's recall what is a probability distribution. If we have some random value x, it means that we can't predict the exact value of x. Instead, we have some knowledge which values x is more likely to take. Let's imagine that you have taken some test consisting of 5 questions, and you are yet uncertain about your mark for this test. This mark will be our random value x in this example. Imagine that you try to estimate this value. On the horizontal axis, we have all possible results for x from 0 to 5, since the test has 5 equal weighted questions. You are perfectly sure that at least one question you have answered correctly. So the probability of x being 0 you estimate as 0. Now, maybe one correct answer is all you got. This is not very likely, but possible, and you estimate the probability of this as 0.1. 2 correct answers, 0.2, 3, 0.5, 4 correct answers, 0.15, and the probability of all your answers being correct, you estimate as 5% or 0.05. Now, you have your estimation of probability distribution of the discrete random value x. The important part here is that the sum of all probabilities in this distribution is equal to 1, which means that at least one of these marks you will get for sure. In the previous example, random value x had a discrete distribution. Now, what if it has a continuous distribution? What if it can take any value from some interval? There's an infinity of possible values of x in this interval, since there is an infinity of real numbers there. In this case, we can't assign the finite probability to each of these numbers, because in this case, the sum of these probabilities will be infinity, and we need the total sum of all probabilities to be equal to 1. In the case of the continuous distribution, there's no such thing as the probability of each exact value. Instead, we can have the probability of x to belong to some subinterval of the whole set of possible values. And this probability will be the area under the graph of its probability distribution, bounded by this subinterval. This area equals to the integral of the probability distribution on the considered subinterval. And the integral of the probability distribution over the whole interval must again be equal to 1. Now let's return back to wave functions. Both graphs here show some probability distributions for the particle to be detected somewhere in the space. The upper graph is 0 almost everywhere in the space except for a very small area around some point A, where it has a high sharp peak. This graph refers to a situation when we have a good certainty about the particle position. This is what we have when we study particles in the terms of classical physics. In quantum mechanics, we have this type of description for massive particles, because massive particles have this type of probability distribution. In classical physics, we can talk about position as of some point, exact location in the space. But for small enough particles, which we study in quantum mechanics, the probability distribution looks different, like in the lower graph. And the particle position can't be considered as some point in space anymore. Now I want you to recall that the area under the graphs, or the integral of the probability distribution of the particle position over the whole space, must be always equal to 1. Physically, this means that particle that we study exists and can be principally detected somewhere in space. Another thing to recall is that the probability of particle detection somewhere is proportional to the wave function intensity, which is proportional to the squared wave function amplitude. This all means that the wave function of a particle can't be just any function. The integral of the squared wave function over the whole space must be finite. This is why we are going further to narrow our domain of consideration to the square integrable functions.